Hi, Physics One. Mr. Janowski here, recording again from my living room. Hopefully, this is the last time I have to do this, and I'll be back real soon. But anyhow, let's try to get a little bit further in the chapter 6, 7 slides and even start the second homework. So I will minimize myself a little bit here. So, first question: what is the single most important thing you will learn in Physics 1? That is Newton's second law of motion, which is F equals ma. Come on, click. Yeah, F equals ma. So very important. This is my favorite thing in Physics 1, F equals ma. And this is the one thing you absolutely must remember for the rest of your life from Physics 1. Second question: if La Pulga Atomica, which is to say Leo Messi, if he kicks a bowling ball and a football, and the bowling ball has 16 times the mass of the football, and he puts the same amount of force on both of them, how will their accelerations compare? Well, if F equals ma, therefore A equals F over m. So if the football has 1/16th the mass of the bowling ball, the football will accelerate 16 times as much. So that's how that works. Again, that's the picture I want you to kind of like mentally associate with the idea of Newton's second law. Leo Messi kicking a football and Leo Messi kicking a bowling ball. And now time to make a prediction. So I wish I were there in person doing this demonstration, but the situation will not allow. So here's what's going to go on. I'm going to stand on a bathroom scale. It's going to read my weight. And then I'm suddenly going to crouch down. So here's the scale. Here's me. I'm going to stand up. It's going to read my weight. And then suddenly I'm going to do that, crouch down. Um, and what I'm asking you to do is predict how will the needle respond. So this is an analog bathroom scale, not a digital kind. It's the old-fashioned kind with the needle. Um, so if you're watching this individually, think of your answer. How will the needle respond? But if you're watching this in a group, then actually, like if they're putting this up on the TV, then raise your hand. Raise your hand if you believe it is A. The needle will move to the lower numbers first. So raise your hand if you think it's A. How about B? Raise your hand if you think the needle will move to the higher numbers first. And now raise your hand if you think it's C. The needle is not going to move at all since my weight hasn't changed. So hopefully you've made a prediction. And now we'll watch the video and see which one it is. So here's a video I took last year. Me standing on a bathroom scale, right over there was where I was doing it. Standing upright, see it reads around 200, so I'm still working on that number. But yeah, I'm suddenly going to crouch down, and the needle is going to go one way or the other. It's not going to be C. The needle is going to move. So let's see which way it goes. It goes to the lower numbers first, and then it bounces around a little bit. But first, yeah, it definitely went to the lower numbers first. So that may be a little bit surprising. So that's me standing upright and then crouching down, with my camera pointing at the numbers. So yeah, I went to lower numbers first. All right, how about in the opposite situation? So here's another video of me crouched down on the scale with my camera pointing at the numbers, and then I'm going to pop right up. So which do you think it will be? When I pop up, will it move to the lower numbers first? A. Will it move to the higher numbers first? B. Or C, it won't move at all since my weight hasn't changed. Once again, it won't be C. If I start down and pop up, yeah, the needle first goes to the higher numbers. And then after that, it bounces around. So that may be a bit surprising. So why does the bathroom scale respond that way? It's complicated. I'll show you. It's not a quick answer. I'll show you why. So something to keep in mind. Mass is not weight. Mass is a measure of inertia and has units of kilograms, whereas weight is a force. Weight is F sub g, the force due to gravity. And like other forces, it has units of newtons, also pounds, but we're going to use newtons for this. So astronauts experience weightlessness if they're up on the space station going around, but no one ever experiences masslessness. So, for example, this astronaut here, she's pushing on the apple. If she puts a force on that apple, the apple has some reluctance to change its motion. So if she puts a little force in it, it'll start to move. It'll kind of move a lot. Now, if she were to push just as hard on this dude right here in the burgundy shirt, he would also start to move, but he wouldn't move as much as the apple. He's got more weight than the apple. Anyhow, keep this in mind. Mass is not weight. So mass is m. The symbol for mass is little m. It's got units of kilograms, and weight is F sub g. Is the symbol for that, and it's got units of newtons. So there's a formula that relates your weight, F sub g, to your mass and to gravity, little g, and that formula is this. F sub g is equal to m times g, where little g is 9.8 meters per second squared if you're near the surface of the Earth. Now notice little g is now positive 9.8 meters per second squared. When we were doing kinematics, we were always making it negative. Don't worry, gravity is still down, but we're going to handle the downness of gravity a little bit differently. So when you're doing kinematics, little g is minus 9.8 meters per second squared. For the rest of the year, it's going to be positive 9.8 meters per second squared. That may seem a little confusing and unfair, but just go with it. You'll see how this works. So there's another force we need to keep in mind, and that is normal force, F sub n. So F sub n, normal force, is the force between any two objects when they're in contact with each other. So normal in this sense means perpendicular. So hands pushing on hands. This hand is putting a normal force that way, and this hand is putting a normal force that way. So we need to know normal force. Now, this is important because technically scales don't read weight. Sometimes they read weight, but they don't always read your weight. What a scale actually reads is the normal force that it's exerting on the object that is resting on it. That's what the number on the scale is. The scale is telling you how much normal force it's putting on the object that is on top of it. And again, sometimes this will be the weight, and sometimes this will not be the weight. But keep that in mind. Scales read normal force. So this here is Dr. File. I'm kind of in the way here. Let me move down here. Dr. File is a physics professor at Westchester. So when I was getting my teaching cert at Westchester, I took a few physics classes, and I never actually had one with Dr. File. But I did work at the tutoring center. And from working at the tutoring center, I had enough of his students that I learned his way of doing force problems. And his way is a very good way of doing force problems. So in honor of Dr. File, here is Dr. File's 4-step strategy for force problems, TM, trademarked. Of course, my 4-step strategy has 6 steps because I always start with a step ha and finish with a step but here are the steps. So, yeah, start with step here it is in the next ones. Let me get myself out of the way here again. So start with step what are you looking for? What units to expect it to have? Step 1 is always a sketch. The sketch will tell the story. It's going to include things like masses, accelerations, velocities, coefficients of friction. You don't even know what that is yet. Spring constants. You don't know what that is yet either. And other things. Yeah, it's a sketch. It tells you what's going on. Step 2 is no longer variable bank. Step 2 in a force problem is the FBD, the free body diagram. So this comes out of your sketch, and the free body diagram is, in a sense, it is a sketch. The difference is it's a special kind of sketch. Whatever the thing was, you're turning it into a box. So the thing is now a box, and the only thing we're attaching to this box is forces. We're not attaching accelerations, masses, velocities, any of the other things that you might have in your step 1 sketch. Free body diagram only has forces. You'll see how this works. That's annoying that it does that. Okay, step 3 is Newton's second law, which is F equals ma, only now we're going to write it the more precise way. So F equals ma is very pretty and very elegant, but for us it's going to be more useful to write sigma F with a hat, F is wearing a hat, is equal to ma with a hat. A is also wearing a hat. So welcome to physics, where sometimes letters and numbers wear hats. These are vector hats. So here's Dr. File wearing a vector hat. If a number's a vector, you give it a hat. And then you'll see what's going on. Anyhow, step 3 is write Newton's second law. So in step 3, all of your forces and acceleration, they wear hats. And all of your forces get plus together. Regardless of which way they're going, everything is wearing a hat. Everything is getting plus together. And then you do step 4, which step 4 is the math. So math means the first part of math will be taking off the hats and putting in the signs. If the thing is up, when you take off the hat, it gets a plus. If it's down, it gets a minus. In problems that are going left and right, if it's going left, it gets a minus. If it's going right, it gets a plus. you'll see how that works. So I'll show you Dr. File's four-step strategy for force problems doing this problem. So the next couple of slides go through this, but rather than do it that way, let me bring up the Jamboard, and I'll do it like this. This will be more fun. So here's the problem we're going to do. We've got a man standing with a mass of 82 kilograms on a bathroom scale in an elevator. I don't know why he brought a bathroom scale into an elevator, but this is what he did. Now he's standing on the bathroom scale, and the elevator is accelerating upwards at 3.2 meters per second squared. So the question is, what does the scale read in newtons? So first step for me is always step So step is, what are we looking for and what units do we expect it to have? So what does the scale read? Well, remember a few slides ago I told you that scales read normal force. So what we're looking for here is F sub n, sorry, that's an n, is equal to question mark, and it's going to read it in newtons. So that's what's going on. Step one, all year long, is you make a sketch. So what do we got? We have an elevator. There's the scale. Here's the man standing on the scale. It seems to be a very tall elevator for some reason. So he's standing on the scale. He's got a mass of 82 kilograms. And this thing is accelerating upwards at 3.2 meters per second squared. So that's what's going on. That's our sketch. I'll give it speed lines. Let's assume we're going upwards. We know that we're accelerating upwards. We don't actually know that we're going upwards. Velocity could be down, but never mind about that. So there's our sketch. That works. That tells the story. Now, step two. Again, in kinematics, step two would be variable bank. In a force problem, step two is FBD, free body diagram. So what's going to happen here is the man is now a box. So there's that. And there's going to be two forces acting on this man. One of them is the force due to gravity. So that's going down, of course. F sub g is that. And the other force is the normal force. So the man is in contact with the scale. Therefore, the scale is putting a normal force on the man. So we have a normal force going up. Now notice, I'm not adding that his mass is equal to 82 kilograms because his mass is not a force. His weight is a force. His weight is related to his mass. F sub g is equal to mg, but I am not writing his mass. That's not a separate force. That's a very common mistake that people make. So there's my FBD, my free body diagram, and that's it. Only attach forces to the box. Step three is Newton's second law. So Newton's second law is F equals ma, but we're going to add a sigma, meaning the sum of the forces is equal to ma, and we're also going to add the hats. So here's how you draw the hats. It's usually like an arrow with just the one blip. It looks like that with just one point on it. That's how you do it. So yeah, the hats. You may not understand what the hats are for, but trust me, there are hats. So yeah, sigma F, sum of the forces. So where do the sum of the forces, where do I get this information from? Look back at your step two and notice that there are two forces acting on this guy. One of them is the normal force. So I'm going to write F sub n with a hat. And the other force is the force due to gravity. F sub g with a hat. So those are the only two forces. So that's the left side of this. Notice in step three, every force is wearing a hat and everything is plussed together. And the right side is MA, and A is also wearing a hat. Okay. Now on to step four, the math. I guess I'll go back to black for this. You don't give you enough colors in Jamboard. So step four is the math. The first part of the math is take the hats off and put in the signs. So when I take the hat off of F sub n, notice that F sub n is going up. So that gets a plus. F sub g is going down. So when I take the hat off of F sub g, we get a minus sign here. So minus F sub g. is equal to, and then we also have to think about the direction over here on the right side. MA. Okay, well, this guy was accelerating up. So when I take the hat off of A, it stays a plus, so I don't have to write it. So it looks just like that. So here's what I have at this point. F sub n minus F sub g is equal to MA. All right, and remember, I'm trying to solve for F sub n. So to do that, I'm going to add F sub g to both sides. That's going to give me F sub n is equal to MA plus F sub g. All right. Well, m and a are numbers. I know those. That's the mass. That's the acceleration. What about F sub g? I've got a formula for that. This is the formula we just learned a few minutes ago. So I'm going to rewrite this, MA, and when I'm going to rewrite F sub g, I'm going to replace it with mg. So I could group the m's together and then factor and like do, but we don't have to. I'm just going to put in the numbers. It's straightforward enough. Okay, so m is equal to 82.0 kilograms. A is equal to 3.2 meters per second squared, plus this m is still 82 kilograms. And little g, remember, is now positive 9.8 meters per second squared. Gravity is still down, but we handled the downness differently. We made gravity down. We drew the arrow here, and right at this point right here, hopefully you can see the dot on the screen. I think that records. Yeah, when I took the hat off, that's when I made gravity down. So that's how we handled the downness of gravity. Anyhow, we get to this point, and we've got a little bit of calculator work to do here. F sub n is equal to, so 82.0 times 3.2 plus 82.0 times 9.8. And if you do that, you get 1066, the Battle of Hastings. And its units will be newtons. So you put a box around it, and finally we do step, well, we solved for the right thing. Normal force, we gave it the right units, newtons. So that looks good. Is 1066 a reasonable number of newtons for this thing to have? That's hard to tell. It's not like velocity where there's a simple bloody cheetah kind of rule and you can figure it out and use your own experience, because we don't really deal with newtons in our everyday life. So just trust me for now that 1066 newtons is a reasonable number of newtons for a scale to read. So that's Dr. File's 4-step procedure. Now back to the slides. Boop. All right, so the next several slides, this is just, it just goes through what I've just done, explaining all the things. So you can use this for your own reference. And again, 1066 newtons. So the Battle of Hastings, which I ask year after year, people never know what this is. This is when William the Conqueror, basically a French Viking from Normandy, the north of France. It's confusing. He invaded England, and he beat Harold Godwinson. So Harold Godwinson used to be the king of England, but here he is with an arrow going through his eye. See, it says Harold Rex, Harold the king. But then he got an arrow through the eye, and now he's dead. And then William the Conqueror, formerly known as William the Bastard, this is how he became the king of England. And this had a huge effect on the English language and things like that. So there's a little bit of history thrown into your physics lesson. So that's it. That is Dr. File's 4-step procedure. If you feel like it, go ahead and try to do the next problems. These are the problems on homework 2 from this chapter. And honestly, if you don't feel like it, we'll just work on it together when I come back in person. So hopefully you found that helpful, and hopefully I'll see you soon in person. Bye-bye.